So if we find the tan of certain angles, we get certain values. But the interesting thing is, if you find the tan of an acute angle, you'll get a positive number. But if you find the tan of an obtuse angle, like 120 or 135, you'll get a negative number. That's going to be handy for today's lesson because we're talking about positive and negative gradients of lines, and we're talking about their angle of inclination. You know, at what angle do these lines go compared to the horizontal? We'll get to that in a minute, but let's just work out these few values here to drive home the point that we can get both positive and negative answers out of tan depending on the angle size. So tan of 45 is 1. Tan of 135 is -1. Tan of 60 is about 1.732. It's actually exactly the square root of 3, but it's about 1.732 according to the calculator. And tan of 120 degrees is negative 1.732. So if we have acute angles, we can get a positive answer out of our tan. If we have obtuse angles, we can get a negative answer out of our tan. Why does that interest us so much? Because if you look at these two diagrams, I'm going to say that we want to talk about the angle of inclination of these lines. So we want to know at what angle do they go to the horizontal. And we're only interested in this angle that the line makes here with the horizontal. Now that's weird. There are 4 angles created each time a line crosses the x-axis. I'll show you what I mean. 1, 2, 3, 4. 4 angles when that line crossed the x-axis. 1, 2, 3, 4. 4 angles when that line crossed the x-axis. We are only ever interested in the angle that the line makes with the positive direction of the x-axis. If the x-axis heads out that way, right, take the x-axis that's heading that way and come back around until you land, right, going anti-clockwise until you land on the line. That's the angle we're interested in. That's an obtuse angle that's created from the positive direction of the x-axis around to the line. That's an acute angle that's created from the positive direction of the x-axis around to the line. You're only ever going to get an acute angle or an obtuse angle with a line, or else it'll be horizontal or vertical, and we'll leave that for another day. So they're the two drawings that we might be interested in, depending on whether the line creates an acute angle, which we know has a positive gradient, because as we walk from left to right across the number plane, we're going uphill, or an obtuse angle, which we know has a negative gradient, because as we walk from left to right across the number plane, we're going downhill. All right, so here's the crux of today's lesson. We know that when we work out the gradient of a line, we do the rise over the run. So here's a quick diagram. I've picked 2 points, and between those 2 points, we want to know what amount of vertical rise happened for what amount of horizontal run. And the rise over the run was equal to the gradient. You remember that we use the letter M, which stands for Mons, to do with mountains and steepness. But M, the gradient, is the rise over the run. But what's interesting here is that also, if we look at that angle there as being the angle of interest, the side opposite to that angle from trigonometry, we know, is the opposite side. And the side next to it here, we know, is the adjacent side. So instead of rise over run, if you're talking about that angle there, you can say tan theta equals opposite on adjacent from that diagram. But the opposite side is the same as the rise, and the adjacent side is the same as the run. So the opposite over the adjacent here is the same as the rise over the run. Well, if the opposite on adjacent equals to rise over run, then tan theta equals to m. So that's our big formula to get from this. I'm saying the gradient of a line is tan theta. But remember what we said about theta. Theta is the angle the line makes with the positive direction of the x-axis. And you unfold that angle by going anti-clockwise. Angle that the line makes with the positive direction of the x-axis. And that angle unfolds going anti-clockwise. I'm yelling here, capital letters, with the positive direction of the x-axis. We know there's 4 angles created when a line crosses the x-axis. We are interested in the angle that the line makes with the positive direction of the x-axis. Turns out it's the same as the rise over the run. So our formula is that the gradient is equal to tan of that angle theta there. And that angle theta has a special name. That angle theta is the angle of inclination. So theta is the angle of inclination. That's that angle theta there. The angle of inclination is the same as the gradient. All right, well, what does that mean in practice if you're asked some sort of question about it? Well, here's the line y equals x minus 1. You can look at the diagram and tell that the gradient is 1 because if you go here and here, for each one across, you go up 1, right? So you can tell the gradient's 1, but you can also see here the number in front of the x is 1. In other words, the gradient is 1. That means I could tell you that the angle that the line goes up at, the angle of inclination, is tan of theta is equal to 1, right? There's theta in there. We know that m equals tan theta, right? M was 1. If you're asked to find an angle, we know from the trigonometry topic that you've got to press shift. In this case, shift tan of 1 will give you the answer, right? To find theta, we go shift tan of 1. We press equals. Sometimes, if you want it in degrees, minutes, seconds, sometimes you've got to press this as well. But that will get us the answer. Without this, you'll get an answer in decimal degrees. With this, you'll get an answer in degrees, minutes, and seconds. But we know the answer is 45. But shift tan of 1 equals, and the answer is 45. So this line here goes up at an angle of inclination of 45 degrees to the positive direction of the x-axis. That there is 45 degrees. All right, you don't need to have a picture then to be able to work out the angle of inclination of each of the lines, right? You can say that tan theta here is equal to 3 because m was 3. So when you want to find an angle, you go shift. In this case, the trig ratio was tan, so shift tan of 3. Shift tan of 3 equals. And press that bubble button, degrees, minutes, second button, and you get 71 degrees and 34 minutes. The angle that that line goes up is 71 degrees and 34 minutes. This one's got a smaller gradient, 2/3 compared with 3. So it won't be 71 degrees, will it? No, maybe 20 degrees. Let's have a look. Let's work out what the angle would be. Tan theta is equal to m. Now there's our m, 2/3. So what was that? 2/3. Don't tread in it. No, 2/3. So we need to press shift tan of 2/3. So shift tan of 2/3. And we get that theta is equal to 33 degrees and 41 minutes. Oh, it's a bit bigger than what I thought it would be, but I knew it would be less than 71 because 2/3 is nowhere near the size of that gradient of 3. Well, here's a gradient of √3. That's about 1.7. So maybe 50, 60 degrees. Let's have a look and see. We know that tan theta is equal to m, is equal to √3. So to get theta, we go shift tan of √3 equals, and it's 60 degrees. All right. So you can work out the angle of inclination, the angle that a line makes with the positive direction of the x-axis, if you know the gradient of a line, or you can work out the gradient. Here, that's definitely a negative gradient, but they haven't written the equation for me. So I need to work out the equation of that line, and then I can work out what is this angle here, the angle that the line makes with the positive direction of the x-axis. Yes, it's obtuse, but we know that when you do tan of an obtuse angle, you'll get a negative number. And that's great because that's got a negative gradient. All right, so it's pretty easy. If you pick a couple of points, like say that point there and that point there, you can see that for each one across, I went down 2. So the gradient's -2. We've done that before. And tan of the angle of inclination is equal to the gradient, which was -2. So all I need to do now is go shift tan of -2. Shift tan of -2. The answer comes out on my calculator as -63.48, blah, 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 blah. About -63 degrees. What is going on? We have to do 180 minus the 63 degrees. So all you do when you get to this point with one of these lines on this type of calculator is you just plus on 180. We're going to get to this in another topic in Year 10 where we look at angles of any magnitude. So for the time being, just plus on 180 to get the obtuse angle we're after. So I plus on 180 here, and the answer that I get is 116 degrees and 34 minutes. So theta equals 116 degrees and 34 minutes, right? So at the moment we're doing, if the answer is negative, I'm saying plus on 180. More explanation to come in a later topic. So m is -3. Tan theta equals -3. So shift tan of -3 equals. The answer is negative, so I plus on 180. And I get 108 degrees and 26 minutes. That's the angle that that line makes with the positive direction of the x-axis. And finally, the angle that this line makes, this is going to make almost 180 degrees, like around at 150 or something like that, being -1/2. But let's test it out. I need to go shift tan of -1/2. And then it's negative, so I need to add on 180 to get my obtuse angle. And I got theta equals 153 degrees and 26 minutes.